by Hitrik from UCLA, who will tell us about tunneling and Weyl laws for the d-bar operator.
Thank you very much. So I'm extremely grateful to the organizers, to Matteo, to Jeff, to Eugenia, and to Stefan for the kind invitation, for the opportunity for me to speak here. This is truly a great, great pleasure and honor for me. And in this talk, I would like to speak a little bit about some recent observations concerning actually a tunneling problem for a model, and as we shall see, a very simple non-self-adjoint operator. So the new results that I would like to discuss in this talk are joint work with Johannes Sjöstrand and Martin Vogel. But before we get into the actual subject of the tunneling in the non-self-adjoint context, I would like to say a couple of words about some general features of the spectral analysis for non-self-adjoint operators, focusing maybe a little bit on the particular issue of so-called spectral instability, which is one of the characteristic properties which sort of plagues this subject a little bit. So we can start quite generally by considering some operator P, which is closed and densely defined on some complex Hilbert space. And then what we know is that in the self-adjoint case, there's a clear link between the size of the resolvent of the self-adjoint operator and the spectrum. So the spectrum controls the resolvent in the sense that the operator norm is exactly given by the reciprocal of the distance from the spectral parameter to the spectrum. So nothing of this kind is going to be true once the self-adjointness assumption is dropped. In this case, the norm of the resolvent can be much, much larger than the right-hand side, the reciprocal of the distance from Z to the spectrum. And that has many implications. The most immediate one is that the numerical computation of eigenvalues in a non-self-adjoint context could be quite challenging just because these eigenvalues are so very sensitive to small perturbations of the operator. So we can illustrate this sensitivity and consequent spectral instability by considering the following classical picture, which has a long tradition in the subject of non-self-adjoint operators. This picture and the corresponding operator goes back to the analysis carried out by the late Professor Brian Davis at the end of the 1990s. And what we consider in this example is a very simple operator, the so-called Davis operator, or the complex harmonic oscillator, which is simply given by the usual harmonic oscillator, but then you put an I in front of the quadratic potential. The eigenvalues can be computed explicitly. They are simply given by the ordinary eigenvalues of the self-adjoint operator rotated by 45 degrees. But as you try to experiment a little bit and do some numerical computation, you see that as you go a little bit deeper into the complex domain, the numerical instability takes over, and you have some difficulties. So this basically illustrates just how fragile eigenvalues of a non-self-adjoint operator can be deep in the complex domain. So the issue and the phenomenon of spectral instability is, of course, closely related to the theory of solvability or lack of solvability for non-self-adjoint, more generally non-normal partial differential operators. So this is a subject which has a very long and distinguished history in the theory of linear PDE, going back to the fundamental early contributions by Levy and Hermander, and then more recently decisive work by Denker. And also I would like to mention that you can sort of change your point of view a little bit and turn this problem into an opportunity by changing your perspective. And you can actually ask the question, what happens to such a highly unstable non-self-adjoint operator once you subject it to a small random perturbation? So philosophically, it is a little bit in the spirit of what Maxime was discussing yesterday in his talk. You introduce some random perturbation, and then somehow good things are happening. In the context of non-self-adjoint operators, what happens typically, once such a random perturbation is introduced, is that there emerges a very beautiful two-dimensional Weyl law, which describes the distribution of eigenvalues of such randomly perturbed operators. So there is now a considerable body of literature on this approach. It is beautifully summarized in the book by Sjöstrand several years ago, but there are also some more recent important contributions, in particular by Nonen, Mascher, and Vogel, and Isaac Altman, to mention just a few. So we're going to be looking at other kinds of Weyl laws, as we shall see, and I would like to continue a little bit with this introductory part and describe a very basic and robust mechanism for spectral instability that you have in the non-self-adjoint case, looked upon through the point of view of semi-classical analysis. So in this talk, we're going to be working with semi-classical operators throughout. Our main operator will be really, really extremely simple, but for now, in this general discussion, we can consider a fairly arbitrary semi-classical self-adjoint operator of an arbitrary order. So I write it like this. The semi-classical parameter h is small, dx is the standard notation for the imaginary gradient. I have some smooth coefficients, and I could consider this semi-classical differential operator on some manifold. And then to this semi-classical differential operator, we associate the principal symbol in the semi-classical sense. So we replace h dx by psi. So this is following the conventions of semi-classical analysis. And we also keep the leading term in these coefficients that are independent of h. So this is a nice function which lives on the cotangent space of the manifold. And then in this case, if the operator is non-self-adjoint or actually non-normal, then you can construct quasimodes, sharply localized quasimodes for this non-self-adjoint operator. So in Leonid's talk, there were some delocalized quasimodes, but here the mechanism is quite different in the non-self-adjoint case. So the precise result that we shall be referring to throughout this talk is the following. Pick some point in the phase space, x0, psi0, and consider, and assume rather, that this point is chosen so that this Poisson bracket between P and P bar divided by I actually is strictly positive at this point. So this is the standard definition of the Poisson bracket of two functions which live on the cotangent space. X is the position variable, psi is the momentum variable. And then associated to this point, and more precisely to the value that my principal symbol takes at this point, is a quasimode. It's a quasimode for the full non-self-adjoint operator capital P. It depends on H, of course. It is normalized in L2. Smooth, compactly supported function on the manifold, and it is a quasimode in the sense that when my P minus Z acts on U, then it becomes something which vanishes to infinite order in H when measured in L2 or in any other reasonable norm. So this is a quasimode construction that we can have as soon as this bracket is of the right sign. So this is sometimes called Hermander's bracket condition. And indeed, this result goes back to the work of Hermander in the context of solvability theory for non-normal partial differential operators. It was rediscovered by Brian Davis in the context of non-self-adjoint semi-classical Schrödinger operators. And then the link with Hermander's work was pointed out in Zworsky. Zworsky and was developed further in this important work by Denker, Shostak, and Zworsky. So just a very quick illustration to appreciate the significance of this sign condition. We can consider the simplest possible example of a principal symbol, little p, which is just this simple thing in dimension 1. This is nothing else but just the symbol of the annihilation operating in quantum mechanics. Then you compute the bracket. It is strictly positive. It's a constant, in fact. And then, indeed, you have the corresponding state, which is just killed by the annihilation operator. That's just a Gaussian. And philosophically, the construction in the general case, once the bracket condition is satisfied, is not really different from this example in the sense that you try and produce this state by doing a WKB construction. It will be a complex WKB construction in the sense that the phase here is going to be a complex valued function. It is going to be obtained by solving this aconal equation. Actually, we are only going to be solving it to infinite order at the point x0, and our quasimode is going to be basically a Gaussian state concentrated in a small neighborhood of x0, thanks to the crucial property of the solution of this aconal equation, namely that the imaginary part of the Hessian of this thing is strictly positive at x0. And then you correct this thing by also solving a sequence of transport equations for the corresponding amplitude. This is just a normalizing prefactor. So you have this very nice quasimode which just sits there. From the point of view of semi-classical analysis, its wavefront set, the semi-classical wavefront set, if you like, is just at this very point x0, psi0. So you have some non-propagating state. And what this means, if we go back to this condition here, is that if we take some realization of our differential operator with some nice domain, so we can talk about the resolvent, that if the resolvent exists at this point z, then of course it has no other possibility than to be blowing up super polynomially in inverse powers of h. So this is a classical WKB quasimode construction in the non-self-adjoint case. I will talk a little bit now about the analytic case. Okay, so this will be important for motivation and for other purposes. So if we strengthen the assumption on our underlying manifold and demand that it should be analytic, and the coefficients are analytic, then we can actually sharpen the quasimode construction. So the conclusion is still the same. We can produce a family normalized in L2, let's say, but it's a sharper quasimode in the sense that rather than vanishing to infinite order in H, we can actually use the analytic version of the WKB method and make sure that this thing becomes exponentially small in H for some fixed positive constant C. And also the localization property of this quasimode, the micro-localization property, is more precise because we can describe the analytic wavefront set of this quasimode, which is still just this one single point. So this is really something which goes back to the foundational work in analytic microlocal analysis. Sato, Kawai, and Kashiwara. The analytic WKB method was, for example, developed by Sjostrom, and this was described, this particular quasimode construction was described in the same paper by Denker, Sjostrom, Zworsky. So in this case, it's even worse. The resolvent is going to be exponentially large at this point z, provided that it exists there. So you have a huge amount of spectral instability in the neighborhood of Z, Z has absolutely nothing to do with the spectrum. So this is, of course, this failure of the link between the spectrum and the size of the resolvent. But do notice that once we have this condition here, what we can do is that we can consider this self-adjoint operator associated with P minus Z. So we take P minus Z adjoint, P minus Z square root. This is a self-adjoint operator. And of course, I am also going to have a quasi-mode, which is just as precise for the self-adjoint operator. But for a self-adjoint operator, the existence of a quasi-mode is going to tell me that I'm going to have an eigenvalue for this guy here, which is exponentially small. So in other words, the original non-self-adjoint operator is going to have lots of singular values that are exponentially small. So you see what could happen is that you could have a situation where your non-self-adjoint operator has singular values that are much smaller than the eigenvalues, and we're going to exploit that. And actually in this talk, we're going to be interested in counting such singular values for a very simple non-self-adjoint operator. So let me continue for maybe a couple of more minutes with the introduction. So this just to motivate this discussion. We can also think about localization or micro-localization properties of states, which we shall refer to as singular states. These are just eigenfunctions of our self-adjoint operator P star P, or maybe the square root. So now I'm taking my spectral parameter Z to be 0, just for simplicity. We can ask the question, where in the phase space are they concentrated? If we consider quite generally a singular state, so an eigenfunction of this self-adjoint operator inside the energy surface P equals 0. So we can get some basic insight into concentration properties of such states just by quoting standard results from microlocal analysis, and I'm still keeping the analyticity assumption in this discussion, so I'm really stating some well-known facts from the microlocal analytic theory. And the first general result that we can recall is that if we are in the region inside of the energy surface where the bracket is of the opposite sign, so remember, when the bracket was positive, we had the region where quasimodes were living, and that produced blow-up for the resolvent. But if we are in the region where the bracket is of the opposite sign, then at this point, in fact, we do have microlocal analytic regularity in the sense that if my point happens to be outside of the analytic wavefront set of PU, so for instance, U could be such a singular state, then in fact, U is going to be microlocally analytic at this point. So this is a classical result which goes back to the same foundational work of Sato, Kawai, and Kashiwara. There was a new, an independent proof more in the spirit of Sjostran's theory and his approach to analytic microlocal analysis given by Himonas in his thesis. So therefore, from this point of view, keeping this result in mind, we can sort of heuristically at least think about the region where the bracket is negative as the classically forbidden region for our singular states. They have to be, well, decaying if we think about this condition captured by the language of analytic wavefront set as saying that somehow in the phase space, this state exhibits some exponential decay in the neighborhood of the point rho naught. So this is how we should think about this condition. And correspondingly, this should correspond to the classically forbidden region for our system.
Should it be rho 0 not in the wavefront of U, or 0 not in the wavefront?
Rho 0. So I have some point in the energy surface, right? I assume that the bracket at this point is negative. And furthermore, I assume that PU does not contain this point in its analytic wavefront set. And then U itself is going to be regular at this point. So it's just a microlocal state. So when my U is a singular state, and this is exponentially small, so that's okay. Exactly. Thank you. Right. So there is another closely related result that I also wanted to recall, which is a little bit more precise, and it concerns the situation what happens inside of the energy surface when this bracket vanishes. So if I'm now at a point, so we can think, actually I'll draw a picture in just a few minutes, but we can think about regions inside the energy surface where the bracket is positive, bracket is negative, and then I have some set where the bracket vanishes. And here the basic observation is the following, that if the second bracket is not vanishing, then we're okay. Then we still have the analytic regularity, and the theorem of analytic regularity still holds at such points. So this theorem also has a long tradition, not perhaps in the semi-classical analysis, but in the context of classical differential operators with analytic coefficients. It goes back to the work of Kashiwara and Kawai law. And then Himonas actually gave a proof using Sjostran theory, and then together with Maciej Zworski, we gave I would say a more maybe easier to understand proof of this analytic result in the semi-classical context. So our motivation actually was coming from some very concrete problem having to do with some very concrete second-order operators, actually principally scalar systems with analytic coefficients, which arise naturally in the study of the so-called chiral model of twisted bilayer graphene. And then somehow we ran into this condition. It occurs there in a natural way. So we were able to prove this result actually using ideas, very beautiful ideas, which rely on some, of some suggestions of Kashiwara and probably also Tripro. So Tripro's paper somehow remained inaccessible to us. But this work was followed by work by Zworsky together with Jean Kaitao, where they considered even more degenerate cases where the second bracket could also be zero, and then you eventually reach some non-vanishing bracket of higher order, and if the order is even, basically, you would like to conclude that you still have analytic regularity at such a point. So our focus was on the semi-classical two-dimensional case for quite particular operators. And then, inspired by these developments, Sjöstrand actually produced an independent and more recent proof. And probably, if you want to have a more unified understanding of what happens in more degenerate situations where you go to higher order brackets, then perhaps Sjöstrand's proof, which unfortunately is still unpublished, is the one that could perhaps indicate some way in which this can be pushed. Okay, so I'll skip this. This is just to illustrate. This is the particular operator that we were interested in the joint work with Zworsky. So this comes from some very nice problem in condensed matter physics. And then somehow we were able to use this microlocal result, assuming that this second non-vanishing bracket holds not just at a point in the phase space, but in the entire fiber above some point down in the configuration space. And then this microlocal exponential decay could in fact be translated into a result about local exponential decay of honest solutions to some PDE in the semi-classical limit. Okay, so I'll skip that. So I would like to finish this introduction by saying maybe one word about the heuristic picture, and maybe drawing this picture on the blackboard for later references. So we can keep in mind, in view of this, we can keep in mind the following heuristic picture in dimension 2. So in dimension 2, we had our non-self-adjoint operator. We assumed that the corresponding energy surface is a compact subset of the cotangent space. Furthermore, we assume that it is given by two equations that have linearly independent differentials. So my dimension 2, so the cotangent space is 4-dimensional. My energy surface is of dimension 2. And then basically what we have is the following picture here. We have the region where the bracket is positive. This is the classically allowed region, or at least heuristically speaking, this is supposed to be a classically allowed region for singular states associated to singular values that are exponentially small. So this is the region where this bracket is positive. Then we have the classically forbidden region where the bracket is of the opposite sign. And then, in the nicest possible situation, I have some separating interface. So let's assume that this curve here, this gamma, where the bracket vanishes. So this is the picture inside the energy surface. So let's assume that this Poisson bracket vanishes on this curve to the first order. So this is really a nice, smooth, one-dimensional curve, which separates these two regions. And then what we would like to do, and this is completely heuristic, but we shall be coming back to these heuristics in the main part of the talk, we would like to view the problem of studying exponentially small singular values for a typical analytic non-self-adjoint operator as some kind of a quantum tunneling problem where we try to connect points here in the classically allowed region to points in the classically forbidden region by some path in the complexification of the cotangent space. So this, of course, is entirely non-rigorous, but I would like to finish this introduction by just mentioning that, of course, the study of tunneling has a long and distinguished tradition in the context of self-adjoint semi-classical operators, in particular in the semi-classical setting of Schrödinger operators. It was developed in a series of fundamental works by Bernard Fer and Johannes Sjöstrand in the 80s, also by Barry Simon. I will give more recent references a little bit later, related to more recent work done on the tunneling in the context of magnetic Schrödinger operators in the self-adjoint case. But for now, I would just like to mention that what was at the origin of the work that I'm presenting today is a very nice paper by my collaborators, Sjöstrand and Vogel, where they looked at essentially the same model problem that we are going to be looking at, but with some additional assumptions which allowed for a separation of variables argument. So the two-dimensional problem, and we are going to be working in dimension 2, was basically reduced to a family of one-dimensional problems, and then very precise results, fine results, were established by these authors. So we wanted to go beyond the case when you would be able to separate variables and consider more general model problems. So as you will see, to some extent we succeeded, but they basically at the price of making our results, I would say, a little bit less explicit. But that work certainly was the starting point for our collaboration. And now I would like to maybe proceed with the main part of the talk and talk about this particular model tunneling problem, which involves the D-bar operator. Okay, so throughout this talk, we're going to be working in dimension 2, and actually my underlying manifold is just going to be the standard two-dimensional torus. I will denote it by M, and we shall think about this two-dimensional torus. We'll equip it with the standard complex structure, if you like. At this point, actually, we have, I think, verified enough so that I could confidently say that everything that I'm going to describe in this part of the talk works when the torus is replaced by an arbitrary compact Riemann surface. But for the presentational purposes, we'll just stick to the case of the torus. Some things become a little easier to present in the torus case, but the results themselves do hold when M is just an arbitrary compact Riemann surface. And then the operator that we're going to be studying, and that's the same operator that was considered by Schostand and Vogel, is nothing else but just a D-bar operator. So that's a standard D-bar on the torus. Well, semi-classical, and then I just conjugate this operator by an exponential weight. I give myself some function phi, some real valued, non-constant function on the torus, and I consider this conjugated operator, we shall denote by p. So this is a little bit in the spirit of the usual Karleman-Hermander, if you like, approach to the D-bar operator, where you try to prove some weight, exponentially weighted L2 estimates. So you consider weights like this. So this is just this very simple operator. First order semi-classical operator. We view it as an unbounded operator on L2. It has some nice domain. We can look at the corresponding adjoint. So for the adjoint, what we do, we just interchange the order here of the weights, and then HD bar conjugated gives me minus HD. So this is the conjugated operator, the adjoint operator. And then we can introduce the symbols, just like we did in a very explicit and simple way in this situation. So here we use the standard coordinates on the cotangent space of the torus, x, y, xi, and eta. And it's practical for the computations to try to work as much as possible in complex coordinates, use the complex notation. So that's z, the standard variable, complex variable on the torus. Xi is the dual variable to x, eta is the dual variable to y. So it's convenient to introduce this complex cotangent variable zeta. This 1/2 is just for convenience of computations. And then what is nice about this particular coordinates is that my standard symplectic form on the cotangent space of my torus, which is this, has this nice expression in terms of the variable z zeta bar, z bar and zeta bar. So you can easily read off the corresponding expression for the Poisson bracket of two observables on the cotangent space that are naturally expressed as functions of z bar, zeta bar. So it is something like this. So you go ahead and compute. So we would like to compute this bracket, which somehow separates our energy surface into two regions. And in this case, it's really very simple. The bracket is given by a function which only depends on the base variable z, and it is nothing else but just a Laplacian of phi. Well, times 1/2 maybe. So from this point of view, this classically allowed region is nothing else but the region where phi is subharmonic, and the classically forbidden region is the region where my phi is superharmonic, and it is somehow the interaction between these two regions that presumably produces the tunnel effect, which leads to the fact that you have a whole bunch of exponentially small singular values for this very simple non-self-adjoint operator. So what we would like to do now is that we would like to introduce this self-adjoint operator. The eigenvalues of this guy here, of course, are the singular values of p, and then we would like to count these eigenvalues of this self-adjoint operator, the singular values of p, that are between 0, and then we give ourselves some strictly positive, independent of h, exponential rate of decay, tau. This tau is strictly positive. It does not exceed the oscillation of the weight over the manifold, and then we try to count how many singular values we have in such an interval as h goes to 0. So this is what this talk is going to be about. And then we would like to maybe view this problem of counting of singular values as the problem of measuring the interaction between these two regions. In this case, it's a very concrete sort of classical analysis interpretation of interaction between regions of subharmonicity and superharmonicity. So maybe one remark about why we restrict the range, the exponential rate of decay to this particular interval, that actually is because if you take tau to be too large, if tau exceeds this oscillation of the weight, then your interval shrinks too much. And actually you can show using elementary methods or quite explicit methods that this interval, as a matter of fact, only contains one singular value. So there's nothing interesting going on here. We just sits at 0. 0 is always a singular value. So we gave a simple argument for that, but I think it is also related to some more sophisticated work, very interesting work by Elfer and Kaczmar, more recent work, and Elfer, Kaczmar, and Persson-Sundquist. Okay, so I mentioned that our results are going to be a little bit less explicit than what we would like, and I would like to start by introducing two notions of, well, auxiliary notions of weights. It turns out that if we want to have a general result giving an upper bound on the number of singular values and a result giving a lower bound on the number of singular values, it is convenient to do so by means of suitable notions of certain auxiliary weight functions. And we shall be referring to these auxiliary weight functions as upper bound weight and the lower bound weight. So this is just some theoretical definition, but we found it convenient to work with these notions systematically. So what is an upper bound weight? So it's just a continuous function on the manifold, real valued. It is sandwiched between, so tau is kept fixed in this discussion. It is sandwiched just pointwise between phi, our exponential weight, and phi minus tau. And then whenever this inequality becomes strict, so psi is strictly smaller than phi, then on this open set, I want my psi to be superharmonic. So this is just the definition, and I'll try to illustrate it with this picture. And there's a corresponding notion of a lower bound weight. It's another continuous function sandwiched between these two guys. And then whenever this lower bound becomes strict, then I have this open set. And on this open set, my psi should be subharmonic. And then associated to any such weight, we introduce what we shall call the contact sets, which are the sets where the set M plus is the contact set between psi and the corresponding upper bound, the set of points where psi is exactly equal to phi. And then there is another contact set, which is not going to be so important. This is the set where my psi assumes its lower bound phi minus tau. So this is a picture, just a schematic picture to illustrate how you can think about these lower and upper bound weights. I owe this picture to Martin, but what is going on in this picture is that, first of all, it is a one-dimensional picture. So we should really imagine that this corresponds to some situation on the two-dimensional torus. So what I have in this dashed line here is the curve given by this function phi. This is the convex part of the curve, so that should correspond to the region of subharmonicity for my phi. Here the curve becomes concave, so this should correspond to the region where my phi becomes superharmonic. And then somewhere here, I have the inflection point where the curvature changes sign. And then I have the contact set, where my psi, this upper bound weight, is exactly equal to phi. And then what should happen outside of this set is that it should be superharmonic. So here it is given by the straight line. So straight line means exactly harmonic. So harmonic, and then it enters the region where phi itself becomes superharmonic, and then it is also superharmonic. And actually in this picture, this psi is simultaneously an upper bound weight and a lower bound weight, because if we consider the behavior of this psi away from the second contact set, it's still harmonic here, and then it just becomes subharmonic in this region when phi itself becomes subharmonic. So this is just a schematic illustration. So at this point, it's just a notion. We can have a notion of an upper bound weight independently of the notion of a lower bound weight. And what we found convenient is to use these two notions to formulate the following first result, which is going to give us quite abstract general bounds from above and from below on the number of singular values. Okay, so in this result, in this first theorem, we assume that we are given some upper bound weight. Where it comes from is another matter, and we shall discuss this next. But I would like to state this result first. So we have some upper bound weight, psi ub for upper bound, some continuous function. And then we assume that this region, so I'll come back to this, so this is not completely unimportant. We'll assume that the contact set that this weight makes with phi is contained in the region where my phi is subharmonic. So this is the classically allowed region. And then actually we can estimate the number of singular values of our operator from above by the following expression. So this is some kind of an upper bound type of Weyl loss. We have 1 over 2 pi h. And then I have this measure here, given by the Laplacian of phi. This is just a Lebesgue measure on the torus, LDZ. So what I'm doing, we can think about it as some kind of a computation of the volume of the contact set. So this contact set sits in the region where this is positive, so this is clearly a positive quantity. It's a compact set. The interior is assumed to be non-empty in any case, so it's a nice set of positive measure, and this is going to give us the coefficient in this Weyl type up or down, and then I just have some small margin here, some remainder. There is a very similar lower bound that we can have on the number of singular values in the same interval that is expressed with the help of this lower bound weight, psi LB. We only have to throw in an additional assumption that psi LB should be continuous, or Lipschitz continuous to be more precise, and then as you can see there is a lower bound which is very much like this upper bound. The only difference is that I have this interior, and then the contact set is now between phi and this lower bound weight. So these are rather general, sort of abstract results. I'll talk a little bit about how this is proved eventually, maybe towards the end of the talk, but this is what gets the subject started. Of course, you can say, well, you know, the value of this result at this point is very questionable because, of course, it depends very much on how we are able to construct such, you know, auxiliary upper bound and lower bound weights in any given situation. So if we are inspired by this picture, which was actually giving us an example of a weight which was simultaneously an upper bound weight and a lower bound weight, then we can try and see what it takes actually to have such a weight, and such weights are going to be referred to as optimal weights. So what does it mean to have an optimal weight? Well, let's think. When can we have a weight which is both an upper bound weight and a lower bound weight? Well, that actually boils down to a free boundary problem. And in the context of free boundary problems, as we learned, it goes under the name of a double obstacle problem. I think it's called double obstacle problem because there are two contact sets, one from above and one from below. So we can consider, quite in abstract way, the following double obstacle problem, where given phi and given the rate of exponential decay tau, we are looking for a solution of the following problem, free boundary problem. So psi should be a continuous function sandwiched between these two guys. And then on the set where psi is strictly smaller than phi, we are going, you know, it's supposed to be superharmonic. So that's a superharmonicity condition. On the set where it's strictly larger than phi minus tau, it's supposed to be subharmonic. So in particular, in the region where it's strictly between these two guys, it's a harmonic function, as was indicated by this straight line on the picture. And then if we are able to solve this free boundary problem, then it means that we do have a weight to which we can, at least in principle, apply the previous theorem and have an upper bound and a lower bound. And of course, what happens is that in this theorem, if you have one and the same psi, then basically it means that you get the Weyl asymptotics because the coefficient here is basically the same as the coefficient here. So that's the strategy in the general case for an arbitrary rate of exponential decay. And so the next result tells us that indeed this analysis can be carried out, and we can in fact obtain an optimal weight as a solution of this double obstacle problem. The only assumption that we make is that along the set where the Laplacian of phi vanishes, so this is exactly this set, right? The separating interface between these two regions, it vanishes to the first order. So it's really, this set really is really a nice curve sitting inside the doors, or maybe finitely many curves. So assuming that this condition is fulfilled, then the theorem is that in fact this problem has a unique solution which has optimal regularity of plus C11 in fact, and then all these additional properties that we needed in order to be able to apply the previous theorem about the contact sets being contained, for example, in the region of strict subharmonicity of phi, are satisfied. They are non-empty sets. The boundaries, the free boundaries of the contact sets are of measure 0. So what this means is that we can combine the two theorems together and write down, at least in principle, a Weyl law for the number of exponentially small singular values. It is a little bit implicit, this Weyl law, just because we are not analyzing properties of the solution to this free boundary problem, but at least what we can say is that we do get Weyl asymptotics for the number of singular values of our non-self-adjoint operator. This is just d bar acting on an exponentially weighted space. And what happens here is that the only assumption that we need is that this separating thing is a nice smooth curve or a collection of such curves. And then the Weyl law is then given by this kind of expression. So we have 1 over 2 pi h. Then I have this coefficient where I'm integrating the same measure as before, and my domain of integration is now given by the contact set between phi and the optimal weight, which comes from the analysis of this free boundary problem. So this expression actually has a nice phase space interpretation. Let me just mention it very quickly. So what we can do is that associated to our weight phi, we can introduce some natural submanifold which sits inside of the holomorphic cotangent bundle of our torus. Of course, it's trivial in this case, but on a Riemann surface, for example, it would be written down like this. Nothing else but just a graph of the holomorphic derivative of phi times some harmless factor. So what is nice about this submanifold is that this is a complex symplectic manifold, so it carries a natural complex symplectic form denoted by sigma c, and then this submanifold is just Lagrangian with respect to the imaginary part of this thing. And so this integral here, which is giving us the coefficient in the leading term in the Weyl law, is nothing else but just the volume, the phase space volume of the restriction of this complex symplectic form to lambda phi, computed over the contact set of the optimal weight when we just lift this thing and consider it as a subset of lambda phi. Lambda phi projects down to the base. Okay, so actually I mentioned that the starting point of this work was a paper by Schottland and Vogel where they analyzed exactly that problem and actually arrived at this Weyl asymptotics. It was more explicit just because the function phi here was only depending on one of the two variables. So in some sense, this is the picture that you saw in dimension 1, and then the authors were able to separate variables and still use some fine analysis in dimension 1, involving some ideas going back to the work of Elfer and Schottland and the Witten complex. But the result was actually the same. So I mean, it was formulated slightly differently, and there was no mention of the free boundary problem just because this function psi could be worked out explicitly. But this is consistent with what was obtained in the previous work. Okay, so this is maybe nice, but it's not as explicit, and in particular, we still know very little. Excuse me. We know very little about the nature of the contact set between phi and this optimal weight psi, which somehow comes to us from some abstract general PD analysis of this free boundary problem. So the last result that I would like to state, or maybe next to last result, is an attempt to make this Weyl asymptotics a little bit more explicit. And one such regime where we can understand the Weyl asymptotics more explicitly is the regime when my rate of exponential decay becomes small. In this case, it turns out that to carry out this analysis, we have to work in a very small region around the curve where the Laplacian of phi vanishes, and we can actually analyze the coefficient, the leading coefficient in Weyl asymptotics a little bit more precisely. So my tau is now going to be small, but independent of h, and then it's more practical, it turns out to be more practical, to introduce another small parameter, which is related to tau like this. So epsilon is basically cubic root of tau. And then we can actually make the coefficient, the leading coefficient in the Weyl law, a little bit more explicit. Let's neglect this. So n is a large fixed number. So this is some small correction term, which actually is uniform in h. And then what I have here is this principal contribution to the coefficient in the Weyl law. So I'm still integrating the same measure as before. I'm computing the volume of a set which should somehow give me an approximation to this compact contact set that we had in the previous theorem. And what happens is that when tau is getting small, then this contact set likes to be fairly close to the region, entire region, which is classically allowed. Just the whole region where my function phi is strictly subharmonic. It's not exactly that, but the leading order, the leading coefficient here is exactly this integral of the Laplacian over the whole set where my phi is strictly subharmonic. And then there is a strictly negative correction, right? So we take away some part of the boundary region close to this curve. And this correction is, well, it's tau 2/3. Here you have 1/3. You have some dimensional analysis. But in terms of epsilon, it's just a correction which is quadratic in epsilon. And then you have some boundary contribution. So gamma is just the curve where the Laplacian vanishes. So it is this curve here. And so what is being introduced here is some quadratic term in epsilon. And then what I'm integrating here is some normal derivative of the Laplacian of phi along this boundary curve. And then I have some higher order corrections in epsilon. So this is a result where we try to be fairly explicit as far as the Weyl law. As you can see, there is no uniformity, unfortunately, in this little O of 1 remainder. It refers to the, as tau becomes small. So this O of 1 refers to the semi-classical limit h going to 0. But there is we're not claiming any uniformity of this O of 1 with respect to tau. Okay, so this is for each small tau. So we can extract one very simple, but maybe still of some small interest, consequence of this theorem, which is much less precise, but it's easier to state. So just a simple corollary. Let's say I'm not interested in counting precisely eigenvalues of a certain fixed exponential rate. Let's say I only care about the total number of singular values that are exponentially small. So then we can do the following thing. We can still assume that the set where this Laplacian vanishes is a nice curve, or at least a collection of such curves, so it vanishes to the first order. And then what we can do is that we can consider this kind of a double limit. I know that this goes like 1 over h, so I'm computing first the limit as h goes to 0, and then having computed this limit, I also send the rate of exponential decay to 0. And then you see what emerges here is the coefficient where my measure here is being integrated over the entire region where my function phi is strictly subharmonic. So philosophically, somehow it means that our singular states really want to live in the classically allowed region, and then the limit as the rate of exponential decay goes to 0, somehow they should really fill up this entire region. This is what this corollary suggests. It is probably possible to give a more direct proof of this corollary, not going through the analysis that preceded this slide, and without necessarily getting such a precise result. But this is certainly something that perhaps would be nice to understand also for more general operators. And I will come back to this point a little bit later. Okay. So there is some recent work by Sergei Finsky, which studies the symptotic distribution of exponentially small eigenvalues also in higher dimensions. So it would be interesting to understand the links between these results and these more recent developments in the complex geometry. Okay, so in the remaining minutes, I would like to say a couple of words about some of the aspects of proofs that go into some of these results, and maybe just to maybe motivate the usefulness of the notion of these upper bound weights and lower bound weights, I'll talk a little bit about counting singular values and estimating their number from above. So this already contains some ingredients of our analysis, but before I do that, I promised that I was going to give more references concerning the more recent work on magnetic tunneling. So our motivation was a little bit different. We weren't necessarily motivated by works on tunneling in the magnetic case, but nevertheless, if we do consider the operator that, whose eigenvalues we consider, it certainly looks very much like a magnetic Laplacian, and magnetic tunneling effects have been studied recently for such magnetic Schrödinger operators in a significant number of works. I would particularly like to mention the work by Elfer, Kovarik, and Persson-Sundquist. This is a work which considers the case when the magnetic field changes sign. So in this case, that would be exactly like our Laplacian of phi changing sign, which is the effect that produces all these exponentially small singular values. And then there are some more recent contributions by Pfefferman, Shapiro, Weinstein, Elfer, Kaczmar, Sundquist, Fournet, Morin, Raimond, and then the most recent work that I'm aware of by Fournet, Guédez-Pontonneau, Morin, and Raymond. So there we have some more things to understand how these two points of view are related. So now I would like to perhaps say some words about some of the ideas of the proofs. So we are going to talk a little bit about proofs of the upper bound on the number of singular values that are exponentially small, and as you can see, our operator is just d bar acting on some exponentially weighted space, so it is no surprise that the basic role in the proof, at least to get started, is played by the classical estimates of Karlman and Hermander, where we prove some a priori estimates for d bar. So we can state the first proposition in the following way. M could be a torus or a Riemann surface, take some open subset of it, and then let's assume that the exterior is non-empty. I have a superharmonic function given inside of this open set, and take some small neighborhood of the boundary of this open set. And then we have the following a priori estimate. For every epsilon and every open neighborhood, we can control an arbitrary function u in this exponentially weighted space with respect to the weight psi, essentially by the corresponding control of d bar in the same exponentially weighted space. And then there is a contribution, a similar type contribution, coming from the small neighborhood of the boundary. So usually when we study exponentially weighted L2 estimates for d bar, it's always with a subharmonic weight. For example, if you look at how Hermander treats the d bar operator. But that's because typically when you are interested in the d bar problem, you would like to have some existence theorem for d bar. So you are really looking at the estimates for the adjoint. And then for the adjoint, you do have a condition of subharmonicity of the weight. So here we're directly developing weighted estimates for d bar itself, so it is natural to assume that our weight is superharmonic, and the proof is completely standard. That's what we always do. Namely, we just consider the d bar operator, we conjugate it by this exponential weight, which is assumed to be strictly superharmonic in this open set. We have the adjoint, and then we compute the commutator. In this case, we compute the commutator between the adjoint and the operator itself. And this commutator has the good sign exactly thanks to the superharmonicity assumption on our weight, provided that the weight is sufficiently regular. So that means that we can get an a priori estimate for the conjugated operator directly from the commutator. And then this is how we can get this estimate. So this is really standard, and it works on a Riemann surface without any problems. You have to work maybe a little bit more, but this really works nicely on a Riemann surface. And of course, it's also well known that Hermander's estimate do work on more general complex manifolds. So how are we going to use this general Hermander type a priori estimate? Well, let's take a singular value of our operator P, or equivalently, if I don't like to think about P acting on L2, I can just think about my original d-bar operator acting on this exponentially weighted space. And let's consider the associated singular state, which is associated to this operator. So it is normalized in the corresponding exponentially weighted space, which we denote by L2 phi. So this is the normalization condition. And knowing that it is a singular state associated to this singular value, it means that this thing here is exponentially small. The exponential decay rate is exactly tau. And then we can just use the previous proposition when our open set is the region where my upper bound weight is strictly smaller than phi. So the fact that psi is superharmonic on this set is the definition of an upper bound weight. And then what this means, if we just apply the previous proposition, it means that my singular state grows essentially like e to the psi over h. But psi is smaller than phi in this set. So it means that my u decays exponentially inside of this open set. It's like having a classically forbidden region for our singular states. So what does it mean? It means that my it means that my u rather becomes concentrated to the complement of this set. But that's exactly what we call the contact set between psi and the function phi. It is a compact set that is denoted like this. And so away from an arbitrary neighborhood of this thing, my u is exponentially small when viewed as a normalized element of the weighted space L2 phi. Okay, so what this means is that thanks to this Hermander type estimate, we can localize the problem to a very small neighborhood of this contact set. And now we can use the subharmonicity of the function phi in a neighborhood of this contact set. So what do? Well, we just introduce all the exponentially small singular values that we care about in a given interval, and let's also consider the corresponding orthonormal system of eigenfunctions associated to these singular values. And let's just consider the orthogonal projection, which projects onto the linear span of these eigenstates. So what we would like to estimate at this point from above is just the trace of this orthogonal projection, right? That counts how many singular values we are going to have. And here is what we do. So we know that my states, my EJs, are localized to a very small neighborhood of this contact set, but this contact set lives inside the region where phi is strictly subharmonic. So take some small neighborhood of this set, comfortably contained inside of this open set, and take some cutoff function. Okay? And then we introduce the classical object in complex analysis, which actually plays the main role both in the proof of the upper and lower bounds, namely the classical Bergman projection. We have this open neighborhood of the contact set. We have this exponentially weighted space L2 phi, and then we consider the classical Bergman projection, which is nothing else but just an orthogonal projection from this exponentially weighted L2 space down to the subspace consisting of holomorphic functions. So what is great about the Bergman projection in this case is that there's a very simple link between the projection and the d-bar. So you use the standard Hermander's estimate, which we don't have to prove because they're already well known, of course, even in the context of Riemann surfaces. And what you conclude quickly is that once you put cutoffs to the right and to the left of this Bergman projection, then you have an operator which is very nice, chi, pi, chi, and each of these singular states basically serves as an approximate eigenvector of this operator, and the corresponding eigenvalue is 1. So that's very easy to prove, thanks to Hermander's estimates. So we are interested in counting the total number of these guys, but of course, because of this property here, it means that all we have to do to control this number from above is just to estimate the trace class norm of this operator. So this is the operator to which everything boils down, and indeed you can very easily see that this number is just bounded by the trace class norm of this thing. Well, the trace class norm is the same thing as the trace, because it is a self-adjoint positive operator. So at the end of the day, all we need to do is just to do some trace computation. We have to compute the trace of the Bergman projection with some cutoffs sitting to the right and to the left. So how can this computation be done? Well, the main observation here now is that this chi is localizing us to the region where my phi is strictly subharmonic. This is the good region, the classically allowed region. And in the classically allowed region, we can actually, basically, essentially, as a black box, use the classical celebrated result, which usually goes under the name of the Kotlin-Zeldich expansion for the Bergman kernel. So I would like to spend maybe a few minutes just reminding you of how that goes, just because it is so beautiful, and also it relates to some other, which in my opinion, interesting related recent work. So the main point is that in this region of strict subharmonicity of the weight, the Bergman projection is very well understood and has been very well understood for quite some time. So more specifically, what you do, you introduce the kernel of this orthogonal projection. You call it the Bergman kernel, which of course has been studied in a large number of works. It is a holomorphic function of x, and actually anti-holomorphic function of y. So I write it like this: a holomorphic function of x and y bar. And then, going back to the work of Kotlin and Zeldich in the late 90s, it has been well known that just knowing that the weight is smooth, the kernel K has a complete asymptotic expansion just locally. So we can formulate the corresponding local asymptotic expansion of this kernel in the following way. Pick some point x0 in our open set, and then introduce what we usually call the polarization of the weight. We think about the weight as living on a small open set in the complex plane, which we view as as an anti-diagonal in C2, and of that anti-diagonal, we introduce an almost holomorphic extension. So just take a function psi, which restricts to phi on the anti-diagonal, and then it satisfies the Cauchy-Riemann equations to the infinite order along the anti-diagonal. That's the almost holomorphic extension as it was introduced by Kerwander, and then of course used by Emilian Schosten, Delfer Schosten, and many important works. So here it is extremely nice to do that, and the simplest version of a classical theorem of Kotlin and Zeldich basically tells us that there is a simple, very simple WKB approximation that you can write down for the Bergman kernel. The role of the phase is played exactly by this polarization, and there is some amplitude. There is a classical elliptic symbol, which has a complete asymptotic expansion in integer powers of h. These guys here, these AJs, are smooth functions. Just like psi, they're holomorphic to infinite order along the anti-diagonal, and the degree of quality of approximation is O of h infinity, so that's in the smooth case. So this result really has a long and distinguished tradition. It was proved by Kotlin and Zeldich in the late 90s, but it relies on the fundamental work done in the 70s by Pfefferman, Butedeman, Weyl, and Schostrand. So actually the original approaches of Kotlin and Zeldich did rely on the work of Butedeman, Weyl, and Schostrand, and then more direct approaches were developed more recently, including a very nice paper by Behrman, Berndsen, and Schostrand. And more recently, I should say, just in passing, because it is perhaps relevant to some other developments, is that there have been recent attempts to improve the understanding of the asymptotic expansion of the Bergman kernels when we assume more about the function phi. So for example, if phi is not just smooth, but real analytic, then there was some recent very important work by Delaporte and Ruby, Schostrand, von Gogh, showing that in fact sometimes this can be sharpened, assuming that phi is real analytic, and this O of h infinity remainder could be sharpened to something which is exponentially small. So that's the case of analytic weight. And I would also like to mention that as soon as you have some results in the C infinity case and some results in the analytic case, it's always interesting to investigate the intermediate cases and the very precise analysis in the important but a little bit mysterious and elusive Gevrey case was developed by Haoran Chong and Hang Shu. But here we only need the classical results of Kotlin and Zeldich, and actually what we need most of all for the computation of the trace is the explicit expression for the leading term in the expansion of the amplitude, the A0. So this A0 can be computed in any number of ways, and actually what you find is that it is given by this very nice expression. It's just a Laplacian of the weight, and then there is some normalizing factor. So what this means is that you can basically, for the purposes of computing the trace, you can just replace the honest orthogonal projection by its Kotlin-Zeldich approximation. You show that you commit only a negligible error in the trace class norm, and then you replace pi, the honest orthogonal projection, by something which is very explicit and for which the computation of the trace is trivial. So at the end of the day, you get this kind of an upper bound. Remember that chi was just a cutoff, localizing us to a small neighborhood of the contact set. So we send chi to 1 point twice, and then at least this gives us an upper bound. So this is how we prove an upper bound on the number of singular values, assuming that we have an upper bound weight. For the lower bound, actually, it's a very similar type of argument. The Catlin-Zeldich parametrics is still fundamental for the lower bound. And perhaps in the remaining couple of minutes, I would just like to say, going back to the last result that I stated, so maybe this result. So this result actually, which is quite, we tried to make this as explicit as we could, which is relevant in the case of small rates of exponential decay. I just wanted to say that it is being proved not by analyzing the solution of the boundary, of the free boundary problem directly, actually. So at the end of the day, we do not analyze the solution of the free boundary problem in the regime of small tau, but rather we construct essentially by hand, using a fairly explicit adiabatic type construction, an upper bound weight and the lower bound weight separately, essentially working in a very small, thin band around the curve where the Laplacian vanishes. The width of the band in the notation of the theorem is exactly epsilon. And then you show that you have still two different weights, one upper bound weight and one lower bound weight. But in the regime of small epsilons, these guys are close together. So you can still apply our first theorem, get some upper bound and get some lower bound. And these bounds, they essentially match. They match modulo some error term, which goes like a large power of epsilon. So this is how this theorem is proved. So it's not necessarily by analyzing the properties of the optimal weight, but rather by constructing these two weights separately. So just to maybe motivate the usefulness of these notions. So finally, I would just like to conclude by mentioning some of the further works and some perspectives that this provides. So I already mentioned that we have pretty much at this point extended the analysis from the torus case to the case of an arbitrary compact Riemann surface. And then we had some very inspiring exchanges and email exchanges and some discussions with Robert Behrman. And actually, in complex geometry, what people like to do, of course, is to consider complex line bundles over compact complex manifolds, of which Riemann surface is just the simplest case. So in principle, it would be interesting to do it also in higher dimensions. And then what you would like to do is you would like to consider not just a trivial line bundle like we did in this case, but maybe a more general complex line bundle. And then the corresponding change of sign in the Laplacian would have the geometric interpretation of the curvature changing sign. In this case, you still have, or potentially you could have some interesting tunneling problem, and you could still have lots and lots of exponentially small singular values, and it would be nice to extend this analysis to this more geometric setting of high powers of the complex line bundle when the curvature changes sign, possibly even in higher dimensions. And most of all, perhaps it would be interesting now for us to go a little bit further. I mean, this operator was still very simple somehow, for which we try to do these things. So it would be very nice to try and understand the problem of tunneling and exponentially small singular values for more general operators that are non-self-adjoint. And in this case, as you can see, the analyticity was never used in this analysis. But for more general operators, presumably analyticity would be needed. And in particular, at the very least, we would like to see the relation between the total number of such singular values, exponentially small singular values, and the classically allowed region, but not just in the simple model case, but for more general operators where this really has some more genuine phase space interpretation. So thank you very much for your attention. Thank you.
Okay, questions?
If you consider instead of looking at hdz bar plus dz bar
Yes,
pi,
yes.
and you put some function a, which is not necessarily dz bar or something,
Yes.
to obtain result, it's more complicated than still everything.
Yes. Yes, so we haven't, that should be possible, yes, I think. So we would have to, so we would have to consider what corresponds to this picture in this particular case, but it should be computable. So that actually is a very nice, that would be another very nice model problem. I think, so this analysis may extend.
So you do not use so much the fact that you have this conjugation by exponential
Yes,
of pi.
yes. I would have to be a little bit careful, but it's definitely definitely an interesting interesting example to consider. At least what we would like to do, for more general operators is maybe, the fact that when tau, this rate of exponential decay, gets bigger, the results become less explicit. So maybe the problem has a chance of being better understood in this more asymptotic regime, because what happens in the case when tau is small is that we can work essentially asymptotically and somehow even avoid, because analyzing this free boundary problem in the case of arbitrary tau and do it asymptotically is probably difficult. But when tau is small, then we can probably handle more general classes of operators, including this one.
What do you know about the eigenfunctions, these singular eigenfunctions?
So we already use some localization properties. For example, we use the fact that they all have to live in a closed neighborhood, in a small neighborhood of what we call the contact set. And this played a role in the proof of what happened.
So the contact set is
contact set is just a set where so we have this additional weight psi. This is just a set where these guys are equal.
But
So they leave.
In your picture, is it contact set? Is in the
Yes.
sigma plus? Is it
Yes.
sigma plus?
Yes.
Or
Let me go back. Yes. Thank you. That's a good point. So this is the contact set, and it sits in this picture. It sits where it's supposed to be. It sits in the region where phi is subharmonic.
So the picture, it's where is it? Is it below? Is it on the projection of the left part of the picture?
Oh, you mean in the general picture? So in the general, so this is, this has not been developed in the case of general operators, but for the G bar, that would be the relevant picture. So this is our context, and then our states, they are concentrated to a small neighborhood, which is why we can essentially count them, because they live in the region where the Bergman projection basically works as the identity when acting in these states. So we can.
But usually, they are really localized like packets, or they spread out throughout the first?
So this we don't prove. I mean, we show that they exponentially decay away from any neighborhood of M.
Yes.
You mentioned the relation with the paper I wrote.
Yes.
There is a direct relation between your Laplacian and the Pauli operator.
Let me see. I think I had a formula for the Pauli. So the Pauli operator. So as far as I understand, it's a system, right? So this is the operator that we consider, and this is the Pauli operator, as far as I understand.